Introduction to series. Let's start with the definition of a series. A series is the sum of the terms of a sequence. So recall that a sequence is just a list of numbers. So here we can see the individual terms of a sequence indicated by a sub 1, comma, a sub 2, a sub 3, and the general term being a sub n, and the list continues. A series is now adding up those terms in the sequence. So notice that I have my term a sub 1 plus a sub 2 plus a sub 3 plus all the way up to describing the general term a sub n, and so on. And the shorthand way of describing a series is to use summation notation, which is this sigma here. And down here we have the starting index. So n equals 1 tells us to start at the first term. And here we're going to add up all the terms of the sequence. So I'm going to go all the way out to infinity at all of the terms. And then this is describing the general term. Let's go ahead and take a look at an example. We want to think about what does the following series add up to? So here we have the series 1/2 plus 1/4 plus 1/8 plus 1/16 plus the general term here is 1/2 to the n, and so on. So we have an infinite list of numbers that we're trying to add together. The shorthand way of writing this over here is the sum from n equals 1 to infinity. We're adding infinitely many terms of this general term 1/2 to the n. So this is something that might be hard for some people to wrap their mind around, the fact that an infinite series can equal a finite number. We can add infinitely many things and get a finite number. So let's try to add the terms one at a time to kind of help us wrap our mind around this idea. So I'm going to start kind of boring. I'm going to add the first term, which is really just kind of listing the first term. I'm going to call that S1. The first sum, just the first term, is 1/2. And in decimal form, that's 0.5. And let's think about adding the first two terms together. We're going to call that S2. The sum of the first two terms is 1/2 plus 1/4. As a fraction, that's 3/4. As a decimal, that's 0.75. And we can keep going. We can add the first three terms. Ultimately, we want to add infinitely many terms, but we're starting out with just really concrete sums here. 1/2 plus 1/4 plus 1/8. And I'm just going to jump straight to the decimal value here. That's 0.875. And so we can keep going with this. Let's take a look at a few more. So here I've gone ahead and written out what is S sub 4, adding the first four terms. Turns out that's 0.9375. S sub 5 is 0.96875. At S sub 6, 0.984375. And of course we can continue on. So I'm actually going to go ahead and over here put S sub 7, which is of course S sub 6 plus the next term. This is 1/64, so it would be 1/128. I'm going to go ahead and give you that value. That's 0.9921875. And what we just calculated here are called the partial sums of the series, right? It's not the complete sum. It's a partial sum. It's just part of the series. But what we've created, though, is a whole nother sequence. We've created a whole other list to go ahead and analyze. So we can go ahead and look at these outputs here, 0.5, 0.75, 0.875, and so on. So we ended with 0.99, and we can try to determine whether or not that new list, this sequence of partial sums, whether that converges or diverges. So here, for this example, it's reasonable to think, kind of looking at the first 7 partial sums, that this infinite series converges to 1. It looks like I'm getting closer and closer to 1 here. Let's take a look at partial sums in general. In general, partial sums look like, well, S sub 1 is just the first term, a sub 1, but S sub 2 is adding the first two terms, a sub 1 plus a sub 2, and S sub 3 is adding the first three terms, a1 plus a2 plus a3, And so the nth partial sum, S sub n, is adding the first n terms of a sequence. And as these start to get longer, we can write them in summation notation. So here we're going from k equals 1 to n of a sub k. So the partial sums, S sub 1, S sub 2, S sub 3, S sub 4, they themselves make a sequence. This is a list of numbers. So we have this new sequence, S sub n, that will either converge or diverge. Now let's go back and look at that previous example and really try to solidify what we're saying here. So this is an infinite series. I have an infinite list of values that I'm trying to add together. And in order to determine if this infinite list equals a finite number, I considered the partial sums. So we computed the partial sum S1, S2, all the way up to S7, and we basically did a numerical analysis. And we looked at the outputs and we said, well, do these look like they're getting closer and closer to any one number? And the answer was yes, it looked like they were getting closer and closer to 1. Well, we can also visualize these partial sums from that last example on a coordinate system, on a graph, with n on the horizontal axis and S sub n on the vertical axis. So here we have these same values graphed, and we can see that they are getting closer and closer and closer to 1. So we have this numerical analysis and this graphical analysis that are leading us to believe that this infinite list of numbers here is actually going to equal a finite number, and that finite number is 1. But can we confirm this analytically? So can we find a formula for the partial sums for the previous example? Well, the answer is yes, and it's a formula that you may remember from pre-calculus. So essentially we're trying to find a formula for S sub k, adding up the first k terms. So the sum of n equals 1 to k of 1 over 2 to the n, I'm writing it like this so we can maybe remember from pre-calc that this is a geometric series. The formula for this was actually the first term, 1/2, and then 1 minus the common ratio, so 1 minus 1/2 to the k, and then all over 1 minus that common ratio again. And if you're thinking, what? Yeah, it's kind of an obscure formula. And the good news is that we don't typically do this. We don't typically find a formula for the partial sums. Now, if we did, I mean, it's kind of nice because then we can simply take the limit of that formula and confirm analytically that the answer is 1. So this formula right here, which is the general term for our partial sums, if I take the limit as k approaches infinity of that 1/2 to the k, 1 minus 1/2, what's going to happen is that 1/2 to the k as k approaches infinity is going to go to 0. So that piece right there is going to go to 0. So what I have left is 1/2 and then 1 over 1/2. Well, that's 1/2 times 2, which is 1. So we can confirm now analytically that this infinite list of numbers added together is actually 1 because we found, or had from pre-calculus, a formula for this partial sum. But in general, we don't always have that. It's not always necessarily easy to find, but that is sort of the formal way that we can go about finding whether the infinite series converges, and it actually gave us what it converges to by taking the limit of that formula. Let's formalize what we just went through in that last example. Convergence or divergence of an infinite series. If S sub n, so this is the partial sum sequence, if the partial sum sequence S sub n converges to some number L, then we say that the infinite series, the sum of n equals 1 to infinity of A sub n, converges to that same L value. Or, in other words, the infinite series, the sum of n equals 1 to infinity of a sub n is equal to the limit as n approaches infinity of the partial sum formula. Now, similarly, if that partial sum list diverges, then we would say that the corresponding infinite series, the sum of n equals 1 to infinity of a sub n, also diverges. So this whole theorem here is really dependent upon us actually having the formula for the list of partial sums, right? That is what S sub n is. All right, let's look at an example. We want to calculate the sum of the series. This is an infinite series, the sum of n equals 1 to infinity of a sub n. So calculate the sum whose partial sums are given by the formula S sub n equals n squared minus 1 over 4n squared plus 1. So this is incredibly rare. We are actually just given the formula for the partial sums. We don't actually have the formula for the list of numbers that we're adding together. We have a formula for the partial sums of that list. So this is very rare, but it's very nice if we are given that. So we know that the infinite series n equals 1 to infinity of a sub n, that is always equal to the limit as n approaches infinity of the partial sum formula. And we are given that partial sum formula. So n squared minus 1 over 4n squared plus 1. So this right here is S sub n. It is given. Very rarely is it given. And again, that process of finding it is often very complicated. So here, it's really nice. It was given to us. So this sum of the series is whatever the answer to this limit is, which again is also kind of nice because this is the limit of a rational function where the powers match, right? So we have n squared. So towards infinity, right? What's going to happen is that we can just think about the leading coefficients, 1 over 4, as the answer, right? So we can just take those leading coefficients because the powers match. And so that is the answer to not only the limit, but what the actual sum of the series is. So this infinite list of numbers not only converges, but we found that it converges to 1/4. Let's look at another example. Let's compute several partial sums for this infinite series, the sum of n equals 1 to infinity of the square root of n. Does the series seem to converge? So I already have listed here a few partial sums. The first one is just the first term. If I substitute in 1, I get the square root of 1, which is 1. The partial sum S sub 2 is the square root of 1 plus the square root of 2, which is approximately 2.414. The partial sum here, adding the first three terms, square root of 1, square root of 2, square root of 3 added together is about 4.416. So finding S sub 4 is really just the previous sum plus the square root of 4. So we have 4.146, right? And then plus the square root of 4, plus the next term. And that's actually really nice because the square root of 4 is just 2. So, this is about 6.146, adding on that next value. And the whole idea is that we are looking at the outputs of the partial sums as its own sequence and thinking, are those getting closer to any one particular number? Well, these are just going to get bigger and bigger and bigger. If I add on the square root of 5, the square root of 6, the square root of 7, I'm just adding on bigger and bigger numbers. So where does it look like these values are headed? If I consider them as their own sequence, they are headed to infinity. So does the series seem to converge? The answer there is no, right? So it looks like this list is heading off to positive infinity. And in that case, we would say that it looks like it's going to diverge. So no, it appears to diverge. Let's go ahead and take a look at this theorem. This theorem says that if the infinite series, the sum of n equals 1 to infinity of a sub n, converges, then the limit as n approaches infinity of the general term a sub n has to equal 0. So I really want this to be sort of an intuitive statement here. The only way that we can possibly add up infinitely many numbers and get a finite number, which would mean that the series converges, so the only way that that can possibly happen is if the limit of the general term equals 0. That basically means that the numbers, they have to be getting smaller, right? That's the only possible way that an infinite list of numbers can equal a finite number, that the list is getting smaller and smaller. So in that example we just took a look at, the numbers were getting bigger and bigger, so the whole sum was going to go to infinity, so it couldn't possibly converge. So in order to even have a chance to converge, the general term, the limit of that general term going to infinity has to equal 0. So let's take a look at an example. As we saw previously, so the sum of n equals 1 to infinity of 1 over 2 to the n, we saw that that converged. We looked at it numerically, graphically, and then we pulled an old pre-calculus formula and showed analytically that was definitely 1. So what has to happen, or what had to happen, is that the limit as n approaches infinity of 1 over 2 to the n, this theorem says that has to equal 0. And that's true. So here the top is constant and 2 to the n is growing really, really big, so that overall fraction is getting really small and going to 0. So that's a really important understanding of what's happening here. The numbers have to be getting smaller and smaller to even have a chance of that infinite series converging. And so the contrapositive of this theorem is also true, and it's an important test to use to determine if a series diverges. So we're going to go ahead and take a look at that next. All right, we are going to look now at what is called the test for divergence, or informally we refer to it as the nth term test. And it is the contrapositive of the theorem we just looked at. So here's what it tells us. If we're given a series, the sum of n equals 0 to infinity of a sub n, if the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. Then the series diverges. So again, I want us to intuitively understand that. What it's saying is that if the general terms are not getting smaller, then of course the series has to diverge. So the only way an infinite series has a chance at converging, the numbers themselves have to be getting smaller and closer to 0. If that doesn't happen, if the limit of the terms that we're adding together, if those individual terms are not going to 0, then the series has to diverge. So as an example, we're going to show analytically that this infinite series we looked at a second ago diverges. So we kind of said, yeah, it looks like it diverges because we did the partial sum list, but to analytically show that this diverges, we are going to use this test for divergence. And so we're going to go ahead and say that the limit as n approaches infinity of the square root of n is equal to infinity, right? And that limit technically does not exist, right? So it's definitely not 0. And in that case, we're using this test for divergence. So the limit as n approaches infinity of the general term square root of n, it equals infinity, which doesn't exist. So since that's not equal to 0, then we can go ahead and say, so the sum of n equals 1 to infinity of the square root of n diverges by the test for divergence. So this is really the very first test that we are learning, and the very first test that you want to apply to any infinite series that you are being asked whether or not it converges or diverges. So the very first thing you want to do is take a look at the general term and think about, are those individual terms going to 0? If they're going to anything other than 0, then you're done. That infinite series does not converge. It diverges, right? So here, again, the limit as n approaches infinity, the square root of n is equal to infinity. Therefore, right, it does not equal 0. So the infinite series diverges by the test for divergence. Let's pause for a main idea. For an infinite series, the sum of n equals 1 to infinity of a sub n to converge, it is necessary for the sequence of terms a sub n to converge to 0, or the limit as n approaches infinity of a sub n must equal 0. So it is necessary for this to happen in order for the infinite series to converge. Now, it's not the only requirement, but it is necessary for this sequence to converge to 0 in order to even have a chance at converging. Now, for an infinite series to converge as well, the limit as n approaches infinity of the partial sums must converge. But we don't always have a formula for the partial sums. Now here is a major warning. If the limit as n approaches infinity of the general term a sub n does happen to equal 0, that really doesn't tell us anything. This does not mean that the series converges. It just means that the series has a chance to converge. So the nth term test is what we call a failure test only. So if the limit of the general term is anything other than 0, then we can say the series diverges. But if the limit of the general term a sub n does equal 0, doesn't really mean anything, right? This does not mean the series converges. So this is a really, really important point that you should take a second to really think about, because it is probably one of the most common mistakes early on when we talk about the tests for convergence and divergence. Let's take a look at a special series called the Harmonic Series. The Harmonic Series, the sum of n equals 1 to infinity of 1 over n, diverges. Well, notice that the limit as n approaches infinity of the general term 1 over n, that does equal 0. But the actual series itself diverges, and this is one way to show that adding this list is going to end up being infinity. So here's kind of an interesting proof that this infinite series diverges to infinity. And it's kind of a clever grouping kind of situation. So here's what we're doing here. So we're saying this list, right, 1 plus 1/2 plus 1/3 plus 1/4, it's the expansion of the infinite series. What we're going to do is show that this list is definitely greater than, right, bigger than this next list that's below it. So let's kind of look at a couple terms side by side here for a second. Well, the first two terms are identical, 1, 1, 1/2, 1/2. But right here, let's take a look at 1/3 and 1/4. So 1/3 is definitely bigger than 1/4, right? And then 1/4 is equal to 1/4. So hopefully, you know, just comparing these two numbers to these two numbers, you're convinced that 1/3 plus 1/4 is definitely greater than or equal to 1/4 plus 1/4. Well, 1/4 plus 1/4 is equal to 1/2. So now this second list is looking like 1 plus 1/2 plus 1/2. 1/4 plus 1/4 is 2/4, which is 1/2. And we're going to kind of do a similar thing, but with the next 4 terms of the list. So looking at 1/5 plus 1/6 plus 1/7 plus 1/8. And we know for sure that these 4 numbers are greater than these 4 numbers, greater than or equal to, because we replaced 1/5 with 1/8. So 1/5 is definitely bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. And then 1/8 is equal to 1/8. So these three numbers are for sure bigger than these three numbers. So again, the greater than sign holds, right? We're convincing ourselves that this top list of numbers is definitely bigger than this next list of numbers. But 1/8, 1/8, 1/8, 1/8, that's 4/8, which is another 1/2. So we're looking at 1 plus a half, plus a half, plus a half. And we could do this again with the next 8 numbers in the list, right? And we can go ahead and add up 1/16 plus 1/16 plus 1/16 plus 1/16 8 times, and that's going to give us another 1/2, right? And so 1 plus a half plus a half plus a half, those numbers aren't getting any smaller, so this whole sum must be going to infinity. So it's just kind of one interesting way to show that the harmonic series diverges. But what was true? The limit of the general term did go to 0. And notice that that did not confirm that the series converges, because it doesn't necessarily. Knowing that the limit of the general term equals 0 really doesn't tell us anything, right? It doesn't tell us anything. So the test for divergence is only helpful if the limit equals something other than 0. Then the series diverges. But if the limit of the general term equals 0, that doesn't really tell us anything at all. Let's take a look at some examples. For the following series, determine if they diverge by the nth term test, or decide if they might converge. Alright, so for part A, the sum of n equals 1 to infinity of 2n plus 1 all over 3n plus 2. The nth term test, or the test for divergence, has us look at the limit as n approaches infinity of 2n plus 1 over 3n plus 2. On this one, this is a limit at infinity. We can think about the end behavior, the horizontal asymptote that's happening here. And so since the dominant terms have the same power, so the degree is the same on the top and the bottom, end of the first, we can take the coefficients as the answer to the limit, so 2/3, and 2/3 is not 0, right? So these numbers are not approaching 0, which means by the nth term test that the series diverges. So the series diverges by the nth term test. Let's go ahead and look at part B. We have the sum of n equals 1 to infinity of -1 to the n. So let's write out a few of the terms here of this infinite series. So we're starting at 1. If I plug in 1, -1 to the 1 is -1, plus, here, if I plug in 2, -1 squared, that's going to give me +1. Then -1 cubed is going to give me -1, and then +1, and then -1, and so on. So we're just bouncing back and forth between +1 and -1, +1 and -1. So let's now think about the limit as n approaches infinity of -1 to the n. So just looking at the individual numbers and thinking, are they getting closer to any one number? No, right? They're bouncing back and forth between positive and -1. So this limit does not exist, right? So it doesn't equal 0. The limit does not exist. So that means that the series diverges by the nth term test, or again, the test for divergence. And this is kind of an interesting one because sometimes people think, well, isn't this going to converge to 0? Because -1 plus 1 is 0, and -1 plus 1 is 0, and so on and so on. But, you know, what if I group it like this? So in just kind of skipping over the first term, and I start to say, well, +1 plus -1 is 0, and +1 plus -1 is 0. So now all the rest of these terms are going to be 0, and a -1's left over. So isn't this -1? So that's kind of an interesting way of showing that this series diverges as well, right, in sort of a numerical way. Let's move on to part C, the sum of n equals 1 to infinity of e to the n over n. So again, the test for divergence, or the nth term test, has us looking at the limit as n approaches infinity of e to the n over n, the general term. E to the n is an exponential function, which we know is going to grow bigger, faster than this polynomial function on the bottom. So we know that if the top of a fraction is bigger than the bottom, then the whole thing is going to go to infinity, right? Which is definitely not 0. So we know that this series also diverges by the nth term test. And just as a brief reminder, one other way that you can evaluate this limit is you can use L'Hopital's rule, because we have an indeterminate form, we have an infinity over infinity situation, so we can use L'Hopital's rule, put a little LH here, and we can think about this as taking the derivative of the top, derivative of e to the n is e to the n, the derivative of the bottom is just 1, and now, well, e to the n just goes to infinity. So just two different ways of kind of thinking about evaluating this limit at infinity. And then finally, let's take a look at part D, the sum of n equals 1 to infinity of 1 over the square root of n. If I consider the limit as n approaches infinity of 1 over the square root of n, well, the denominator is growing really, really big, while the top is staying constant, and that type of fraction is getting really small. So the limit is 0. The individual terms are getting closer and closer to 0, right? So what does that tell us? Nothing. The series, it might converge, but it might diverge. So really, this doesn't give us a whole lot of information. The series might converge, right? Or diverge, right? We really don't know. There's not enough information yet, right? So we are soon going to learn more techniques for determining whether an infinite series converges or diverges, but this is the first test that you want to use, even though it really only tells you about divergence. Let's wrap it up with a main idea. If the limit as n approaches infinity of the general term a sub n equals 0, then the infinite series, it could converge or it could diverge. We really don't know. But if the limit as n approaches infinity of the general term does not equal 0, equals anything other than 0, then we can conclude that the infinite series diverges, and then we are done. So we will soon learn more techniques, as I said, for determining the convergence or divergence of various series. So we're not going to leave our answer as could converge or could diverge for very long. We're soon going to add a list of techniques so that we can say for certain whether any infinite series we're given either converges or diverges.